Okay, this unit can be broken down into 4 major categories: atomic structure, radioactive decay, periodic trends, and waves. For the next 2 weeks, we're going to be spending our time on atomic structure, breaking down what an atom is and what makes up an atom. Okay, in this unit, or let's just say in this subunit of atomic structure, we're going to talk about what are subatomic particles, what are valence electrons, how do electrons configure themselves, or what we know as electron configuration. Finally, we'll end up with what are isotopes and ions. So our goal or objective for today is to identify and locate the 3 types of subatomic particles with their respective charges. And we need to be able to use the periodic table to predict the number of subatomic particles within an element. In saying all that, let's jump on in and learn about atoms. As stated in a prior video, atoms are considered the smallest substance of matter that still retains the properties of an element. But how did we get to this point? And how can we be sure that atoms make up everything? Well, let's go back into history and give you a brief overview of how scientists discovered atoms and how atoms were founded. Today we're going to talk about 3 scientists, and those 3 scientists had a major impact in chemistry. Their names are John Dalton, Earnest Rutherford, and Neils Bohr. So let's first start off with John Dalton. John Dalton was the first person to publish theories about what atoms looked like and behaved. He had 5 statements that shaped the future of all of chemistry, basically. Scientists after him started basing their observations, basing their knowledge on his postulates or his theories. So let's start breaking down his 5 postulates. His first postulate or statement was that all elements are composed of small particles called atoms. So basically he was saying, hey, every element that we see, it can be broken down into a fundamental unit called an atom. His second postulate or second statement was that all atoms of the same element are identical. Okay, so basically this is saying that all carbon atoms are the exact same. They look alike, they weigh the same, they're equal to each other. Though this may not be true today, for John Dalton's time, that was the best they were going to get. Later this unit, we'll talk about ions and isotopes. But for right now, all you need to know is all atoms are the same to each other. So all carbon atoms are the same as carbon atoms. And then all gold atoms are the same as a gold atom. So his second postulate being that atoms that are identical to each other, so all atoms of the same element are identical to each other, well, then it would make sense that his third postulate would say that different elements are not identical from each other. So for instance, a lithium atom is different than a carbon atom. It may weigh different. It has different properties than a carbon atom. And so that's basically what he's saying, that different elements have different properties. His fourth postulate stated that atoms can combine with each other in whole number ratios. So what does that mean? It means we can't have like half an atom combining with another full atom. So we can't have H 2.5 O instead of H2O. Okay, you got to have full atoms combining with full atoms. We don't want to split atoms because bad things happen when we split atoms. Dalton's final postulate states that chemical reactions occur when atoms separate from each other, are joined back together, or rearranged. So basically when one atom and another atom interact with each other, that's when a chemical reaction is going to occur. Next, we want to talk about Earnest Rutherford. And Earnest Rutherford is famous for his gold foil experiment. Basically, Rutherford's experiment consists of a thin gold sheet. And then he shot really small particles called alpha particles at this gold sheet. He then would record where those alpha particles ended up by having a sensor that encircled the gold sheet. So Rutherford conducted this experiment. He was shooting alpha particles at this gold sheet. He noticed that some of the particles just passed through like he expected. He realized after so many shots that, hey, these particles would bounce off in an odd direction. They wouldn't just pass all the way through. So this made him think about, like, what are these alpha particles doing? What are they hitting? What's causing them to go straight through? What's causing them to bounce off in odd directions? And through this experiment, Earnest Rutherford came up with 2 assumptions that kind of shaped the rest of chemistry. His first assumption was that an atom is mostly made up of empty space. What made him think that? Well, whenever he was shooting that gold foil with the alpha particles, a majority of those alpha particles passed straight through. So they didn't veer off in any weird direction. They didn't bounce off anywhere. They just went straight through. So they must not have come in contact with anything. His second assumption was that these alpha particles, if they are bouncing off in some odd directions, they must be hitting something bigger than themselves. So whether they were bouncing straight back at the machine or off at an angle or whatever, Rutherford thought that because they bounced, that means that they hit something. So because of this, he assumed that an atom has a dense core, and this dense core is massive compared to the atom itself. And this dense core is what he called a nucleus. So the big things from Rutherford: atoms are mostly empty space, and they have a dense core called a nucleus. Finally, we get to Neils Bohr. And Niels Bohr expanded on Rutherford's gold foil experiment. He expanded on just trying to understand atoms more, and his biggest contribution was the planetary orbital model. Basically, this was saying that just like the planets orbit the sun, or he believed that electrons, or small subatomic particles, orbited around the giant massive nucleus. Okay, so with that backstory, now we can talk about atoms and talking about what makes up an atom. From Rutherford's experiment, we can state that an atom has a dense core. A majority of the mass of that atom is located in this core nucleus. This core contains two types of subatomic particles. The first is protons. Protons are positively charged subatomic particles, and they are the identity of an atom. The number of protons are specific for each element, and they never change. So for example, oxygen has 8 protons. No matter what we do, no matter what properties we switch up in oxygen, as long as we have the element oxygen, it is going to have 8 protons. Neutrons are the other thing in the nucleus. So protons and neutrons are in the nucleus. They are neutrally charged subatomic particles. This means they are neither positively charged or negatively charged. The big thing about neutrons is they make up a lot of the mass of the nucleus. So the number of protons plus the number of neutrons is going to be a majority of the mass of the atom. Our third subatomic particle are electrons. Electrons are negatively charged. These electrons, these negatively charged subatomic particles, are found in what we call the electron shell, or these outer orbital layers around atoms. What's significant about electrons? Well, electrons, we'll later learn, are how atoms interact with each other. They give up electrons, they gain electrons. This is how chemical reactions occur. So electrons are huge, but they also vary from atom to atom. So a key thing to know is, unless stated otherwise, an atom is going to be neutrally charged. What does that mean? That means the number of positive charges and the number of negative charges equal each other. Okay, so let's think about this. If we know oxygen. Okay, so if we know oxygen has 8 protons, and we know it's neutrally charged, that means it's going to have the same number of electrons as it does protons. So it's going to have 8 electrons. Okay, so if it's neutral, electrons equal protons. Okay, so now we got that information and we understand like what makes up an atom. We can actually get to applying this to chemistry and applying this to what we'll be learning in class. So if you look at the periodic table, you can see that it's broken down into a lot of different squares. These squares, or periodic squares, contain all the information you need to know about an element and trying to figure out how many subatomic particles it has, what is it made up of. Okay, so we're going to break down how do we read these squares and how what information can we extrapolate from these periodic squares. Well, each periodic square contains an atomic number. This is the number at the very top of the square, and it is also known as the number of protons. So this is the identifier for that atom. So no matter what element we see, if we go look it up in the periodic table and we see on each square, we see the number up top, that number is the number of protons. So for oxygen, oxygen has an atomic number of 8. That means it has 8 protons. Now, like we said earlier, if oxygen is neutral, that number of protons equal the number of electrons. So it would also have 8 electrons. So that's the first thing, the atomic number. Then we have the chemical symbol. The chemical symbol is just the letter, it could be 1 or 2 letters, kind of just represents that element. Instead of having to write out carbon or lithium or something like that 100 times or however many times whenever you're writing an answer, it's just easier in a chemical equation and just in chemistry in general, as much as we use these elements, just to write out the chemical symbol. So this is just a shorthand way of writing and identifying these elements. So we have atomic number, chemical symbol. Now we can go to the atomic mass. The atomic mass is the number at the very bottom of the periodic square. It is usually a decimal number, but does not always have to be. The atomic mass is basically how massive the element is. So we talked earlier about the nucleus being the most massive part of the element. This is basically going to be your mass of your nucleus. So your atomic mass is the number of protons plus the number of neutrons. Okay, so how do we find it? If we're given oxygen, okay, oxygen has 8 protons because its atomic number is 8. In order to find the number of neutrons, we just take the atomic mass and we subtract the number of protons from it. So if I'm not mistaken, oxygen has atomic mass of 16. So 16 minus the atomic number of protons, 8, is going to give me 8 neutrons. Okay, so I said earlier that sometimes these atomic masses can be decimal numbers. For the sake of calculation and for the sake of your own sanity, round these numbers to the nearest whole number, whether that's rounded up or rounded down. From there, you can then find the number of protons and the number of neutrons. This is not the most accurate way of finding them because we do round, but for the sake of our class and for the sake of how precise we need to get, this is going to be what's going to work. Okay, so now that we understand how to read these periodic squares, let's do a couple practice problems first so you can just get a good feel for them. Okay, so the first element we want to practice on today is sulfur. I'm going to have its periodic square represented in our video, but you can just also go look on it on the periodic table and find it. Sulfur, the top number on sulfur is 16. That means its atomic number is 16. That means sulfur has 16 protons. Okay, this is going to be a neutral element because we didn't state otherwise. We didn't say that this is a charged element. So because sulfur is neutral, not only does it have 16 protons, it has 16 electrons. So the chemical symbol for sulfur is S. We also have with sulfur, the atomic mass is the decimal number at the bottom, 32.06 atomic mass units. We can round that to the nearest whole number, which is 32. So in order to find the number of neutrons, all we're going to do is take our 32 and subtract our 16 from it. And that's going to give us 16 neutrons. Okay, so that's sulfur. Let's work a different one. How about zinc? Zinc's chemical symbol is Zn. Okay, its atomic number is 30 and its atomic mass is 65.38. If we break this down, zinc has 30 protons because its atomic number is 30. If it's neutral, then it has 30 electrons. And finally, in order to find the number of neutrons, we take our atomic mass minus our number of protons. So 65.38, or we round that down to 65, minus 30, and that's going to give us 35 neutrons. So zinc has 35 neutrons, 30 protons, and 30 electrons. This time we'll go on the left side of the periodic table. Calcium. Calcium's chemical symbol is Ca. Its atomic number is 20, so that means it has 20 protons. And its atomic mass is 40.078. We can round that down to 40, and if we take our atomic mass minus our protons, that's going to give us 20 neutrons. So calcium has 20 protons, 20 neutrons. If it is neutral, then it also has 20 electrons. Not too bad. Okay, let's do one more just for practice sake. Okay, let's see. Let's do tungsten. Tungsten's chemical symbol is W. Okay, it's number 74 on your periodic table. So the atomic number is 74. That means it has 74 protons. We're going to assume tungsten's neutral at this point, so it also has 74 electrons. Now, its atomic mass is 183.84 atomic mass units. If we round that to the nearest whole number, that's 184. In order to find the number of neutrons, we take our 184 atomic mass units, subtract our number of protons, which is 74, and we're going to get 110 neutrons. Well, that's all I got for you today, and I kind of hope this helps you out and understand subatomic particles a little more, or at least how to understand and read a periodic square from your periodic table. Remember, you can always rewatch this video if you need to, if you didn't get something, or you just need to refresh or review this topic. And saying all that, keep up the good work in the classroom, and I'll see you next time.